Welcome to this explainer. I'm absolutely thrilled you're here today because we're tackling one of the most foundational, fascinating, and honestly widely used concepts in machine learning. We're going to bridge that gap between simple visual intuition, the kind of logic we naturally use every single day, and the hard, rigorous math of decision trees. We'll be pulling apart the nuts and bolts of how these algorithms actually work under the hood, literally translating visual regions into mathematical equations. It's going to be a highly structured, super focused journey, so get comfortable.
Okay, let's dive into this by looking at a highly practical problem, and arguably the most vital problem for any Canadian out there. Imagine you want to build a classifier that predicts whether or not you can go skiing, and you're basing this entirely on just two inputs, the month of the year and your latitude on Earth. That's our data set. Well, if you plot this data out, you immediately run into a fundamental issue. You simply cannot draw a single, straight line to separate the can ski data points from the cannot ski data points. The conditions for skiing exist in these little clustered pockets depending on the hemisphere and the season.
And this really highlights a severe limitation of traditional linear models. Vanilla support vector machines, or generalized linear models, rely on generating a hypothesis function represented by a simple formula, h of x equals theta transpose x. That's essentially drawing a flat line or a plane right through your data. It completely fails on our clustered skiing dataset. Decision trees, on the other hand, are inherently nonlinear. Instead of drawing a single line, they partition the entire input space into what we call disjoint subsets, or regions. Basically, they isolate the data by drawing boxes around the positive and negative spaces.
Section 1. Splitting regions step by step.
So we know it draws boxes, but selecting the perfect regions all at once is computationally intractable. It's just too hard. Instead, decision trees use a method called greedy top-down recursive partitioning. It starts top-down with the entire original input space. Let's call that the parent region. Step 1, the algorithm selects a single feature and a threshold t. For our skiing problem, it might look at location and set a threshold at a latitude of 15. Step 2, it splits that parent region into two child regions based on that exact threshold. Step 3, it picks one of those new child regions and splits it again, maybe this time looking at the time feature and setting a threshold at month 3. It repeats this process recursively, greedily carving up the space piece by piece.
Every time a split occurs, the data gets separated into these two distinct buckets. Child 1 receives all the data points where the feature is less than our threshold t, and child 2 gets everything greater than or equal to t. At the very end of all these recursive splits, the algorithm just stops. These final regions are called leaf nodes, and when a brand new data point lands in one of those leaf nodes, the algorithm makes its predictions simply by looking at the majority class of the training data points trapped inside it.
Section 2, choosing the right loss. Which brings us to a crucial question. We know it splits the data, but how does the algorithm actually know which feature and which threshold make the best split? Well, the entire goal of the algorithm at every single step is captured by one core objective: maximize our decrease in loss. It evaluates a potential split by taking the loss of the parent region and subtracting the weighted loss of the two proposed child regions. It weights those child losses by their cardinality, meaning how many data points are actually in them. By comparing the error before the split to the error after the split, it zeroes in on the specific feature and threshold that gives us the absolute biggest drop in error.
Now, what's really interesting is how we actually define that error or loss. You might think, hey, we should just use misclassification loss, simply count how many points we'd get wrong if we guessed the majority class. But think about its mathematical traits. Misclassification loss is not strictly concave, and it's highly insensitive to shifts in probability. In practice, you could make a split that successfully isolates more positive data points, yet the mathematical decrease in misclassification loss registers as exactly 0. No way, right? To fix this, we use cross-entropy loss. Because cross-entropy is strictly concave, forming a rigid, bull-like mathematical shape, as long as the child regions have different proportions of data and are empty, it practically guarantees a decrease in loss. It is incredibly sensitive.
And because of that incredible sensitivity, cross-entropy is absolutely the gold standard metric for growing classification trees. From an information theoretic perspective, cross-entropy measures the number of bits needed to specify an outcome given a known distribution. When we calculate the reduction in cross-entropy loss from a parent to its children, we call that information gain. We are quite literally measuring how much new information our split has given us about the dataset.
Now, I want to briefly pivot here. Everything we just discussed applies to classification, like predicting ski or no ski. But decision trees are also fantastic for regression, where we're predicting a continuous number, like the exact temperature at a ski resort. The really cool thing is,
The exact same recursive tree growth process applies. The only differences are that the final prediction at the leaf node is the mean average of all its values, rather than a majority vote, and we optimize our splits using squared loss instead of cross-entropy.
Section 3. Controlling tree growth.
Let's shift our focus to real-world engineering and regularization. One massive advantage of decision trees is how beautifully they handle categorical variables. If our location was labeled north, south, or equator, we wouldn't need to mathematically transform that data using one hot encoding, which, as we know, most other algorithms require. The tree just naturally probes subset membership. But there is a huge danger here. If you have a variable with hundreds of categories, the number of possible splits the algorithm has to check is 2 to the power of the number of categories. That makes the math totally intractable computationally and leads straight to massive overfitting.
Overfitting is actually the arch nemesis of the decision tree. So the crucial point is this. If you let a tree grow continuously until every single leaf node contains exactly one training data point, you've created a fully grown tree. Sure, it'll have zero error on your training data, but it will have exceptionally high variance and low bias. It has simply memorized the exact specific noise of your training set. It's like a student who memorized the precise answers to a practice quiz, but completely bombs the final exam when the questions change slightly. It'll perform terribly on new, unseen data.
To maintain generalization and prevent that severe overfitting, we use regularization techniques called stopping heuristics. Basically, we artificially halt the growth of the tree. We might enforce a minimum leaf size, telling the algorithm, hey, don't split a region if it has too few data points. We might enforce a maximum depth, which caps how many consecutive splits from top to bottom are allowed, or we might set a maximum number of nodes, simply limiting the total leaf count of the entire tree. Now, you might be wondering, why not just tell the tree to stop growing if the information gain falls below a certain number? Why not use a minimum loss decrease rule? Well, we avoid this because of higher order interactions. Sometimes, a tree needs to make a mediocre split on one feature to unlock a spectacularly good split on a second feature further down the line. If you terminate early based on a strict loss threshold, you miss those complex interactions entirely. The absolute superior strategy is to grow the tree out fully and then prune away the useless nodes from the bottom up using a completely separate validation set.
Section 4. Practical pros and cons. Let's move into our final evaluation of the algorithm. And this brilliantly illustrates why decision trees are so beloved in production environments. Big O of D. Testing a brand new data point only takes big O of D time, where D is the depth of the tree. The computer literally just traverses down the nodes, asking a few simple true or false questions until it hits a leaf. If the tree is perfectly balanced, that depth is logarithmic. It is a lightning-fast process. Training is also remarkably efficient. To train a tree on n examples with f features to a depth of D, the runtime is O of n of D. By intelligently sorting the data and caching intermediate values, the algorithm actually achieves an amortized runtime of O of 1. That's at each node, per data point, per feature. It's incredibly elegant and scales very, very well for model training. But here is the major fundamental weakness of decision trees. Because they're greedy and because they only look at one single feature at a time to draw perfectly horizontal or vertical boxes, they are absolutely terrible at drawing simple diagonal lines. If your data is perfectly separated by an additive boundary, like feature 1 plus feature 2, a basic linear model draws that diagonal line instantly. A decision tree, however, it cannot capture additive structure. It is forced to build a massive, clunky, high-variance staircase of step-like splits just to approximate a simple diagonal line. Which leaves us with a totally fascinating puzzle. We have an algorithm that is lightning fast, highly interpretable, and excels at carving up complex nonlinear regions, but it's highly prone to overfitting and struggles immensely with simple additive diagonal structures. So if a single tree is this flawed, how might we combine or ensemble hundreds of these trees together to cancel out their weaknesses and build the ultimate predictive algorithm? That is exactly the question you should be asking yourself, and it's where the real magic of modern machine learning begins. Thanks for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.